Hello, this is Dr. Liu. In this video, I will show you how to do a Newton's laws problem with a gardener pulling a cart. Okay, so a gardener is pulling a cart with bags of pebble. Total mass is 170 kilograms across a lawn. His pull at a 35-degree angle above horizontal barely balances the effect of friction, so the cart moves slowly at a constant speed. If he is pulling with 900 newtons of force, then what is the coefficient, frictional coefficient between the tires and the lawn? Okay, so we were given a few numbers. So we have the mass of the total object, and we also have a force that is exerted at an angle, so 35 degrees and 900 newtons. We were also given this constant speed. This constant speed is important. It implies there's no acceleration. Right, so we'll write it down, and also we're asked about frictional coefficient. So let's write down what we have. We have a force from the gardener. Let's use a pull because I don't want to use a lower g. That sounds like a gravitational force. So this force is 900 newtons, and the angle is 35 degrees above the horizontal. And we have a mass 170 kilograms and an acceleration equal to 0. This is constant speed, right? So we have constant speed, so the acceleration is 0. Alright, so let's draw a free body diagram to include all the forces. So I'm just going to use the grid lines. I'll note this doesn't look like a cart, the gardener pulls, right? But this is representative enough of a mass. So we have a mass here, and I want to start drawing my forces all originating from this origin with x and y axis. Let me draw some axes. So this is my x-axis, a bit crooked, but that's okay. It's just showing a direction. This is my y-axis, and that's the origin. So let's first draw the force from the gardener. The gardener is pulling at a 35-degree angle. So let's draw something approximately 35 degrees. So here's the gardener's force, pull. Okay, so after that we should draw gravity because the cart always feels gravity. So there's gravity here, Fg, or you can use another symbol. You can use weight, right? So either way, and then we realize that the cart is on a lawn, so the lawn as a surface is pushing the cart upward as a support. So there's a normal force upward. I'll put an arrow here. Say this is normal force, F normal. Or you can use just capital N. In some texts, capital N is more common than the F sub N. And also there's friction pulling backward. This is a pretty common symbol, Fk, a kinetic friction. This means the object, this cart with pebbles, is moving, so there's a relative motion between the cart and the lawn. So there's this kinetic friction involved. Okay, so 1 force, 2 forces, 3 forces, and 4 forces. We have 4 forces, and we were told that somehow the acceleration is 0. That's okay. So I forgot to put the angle in here. This is that angle, 35 degrees, and also there's a mass m. So let's put m here. Okay. So the next step here is to look at the 4 forces. One of them, this gardener's pull, is not along x or y axis, so it's hard to find this effect. And we will make this force a hypotenuse of this right angle triangle, and we break this force down into its x and y components. We've done that before with vectors. So this amount will be the Fpx, and this amount, which I'll translate over to the axis, is Fpy. Alright, so the Fpx is the Fp 900 newtons times cosine the 35 degree angle. Fpy is Fp times sine of 35 degree angle. So now that we have them broken into components, the x direction has these forces, right? Fp's x component and also friction. Then y direction has three forces: normal force, Fp's component up, and also gravity down. So now that forces are in their respective axes, or decomposing into their respective axes, we can start using Newton's second law. So let's calculate Fpx. This is Fp, P cosine theta p. So it's 900 times cosine 35 degrees. And we'll find the value. We'll just keep on writing. Fpy equals Fp sine theta p, which is 900 times sine 35 degrees. Okay, so let's use our Python calculator. So 900 times cosine 35 degrees that's the x component of the pole, 737, and 900 times sine 35 degrees, that's the y component of the pole, so 516 newtons. So 737 and 516. So here's 737 newtons, 516 newtons. Okay, so we broke down the component the force pull from into its components. So let's now use Newton's second law. Let's use Newton's second law in x direction. So sum of the forces in x is equal to mass acceleration in x, and the sum of the forces will involve this forward component and this friction. So Fpx minus friction equals max, and acceleration 0, that means x and y accelerations are both 0, so this is m times 0, so this is m times 0, so it's equal to 0 regardless of m. And now we have this is 737, so we have 737 minus frictional force equals 0. So we conclude frictional force is equal to 737 newtons. But we were not asked this frictional force, we're asked the frictional coefficient. So let's move this a little further up here. Okay. I just want to move this out of the way of the free body diagram. So if I need the free body diagram, I can easily move it. Okay, so let's go ahead and solve the y direction. So we need to sum the forces in y and equate that with mass acceleration in y. And the sum of the forces, since I have this force decomposed, I have that plus that minus this negative this, right? So I have Fpy plus normal force Fn or n minus gravity Fg or the W, that's equal to mass acceleration y is 0 because the cart only accelerates or moves in the x direction, the y direction has no motion, so this is 0. So Fpy, we have a quantity 516 plus normal force, we don't know, minus gravity. Gravity is mass times acceleration of gravity, is 0. So from here we can solve for normal force, which is the difference between gravity and this pole's y component. and the mass is 170, gravitational constant 9.8, minus 516. Looks like we need our calculator again. Let's bring up the calculator. So 170 times 9.8 minus 516. So we have 1150. Okay, so now we have the normal force. Recall how friction is related to normal force. Kinetic friction is coefficient of friction, kinetic coefficient of friction times normal force. Sometimes this is also written as coefficient times the big N, because here big N and Fn, these are the same normal force. They're just different symbols. Right? So we have coefficient times 1150, and we already know friction from here, 737. Right? So let's just draw this line here. Indicate we already know that. So that leaves the coefficient of friction, which is 737 divided by 1150. Another time to use a calculator. Let's bring it up. So 737 divided by 1150. So we have a coefficient of 0.641. 0.641. And there's actually no unit. This is dimensionless. Okay, you might ask, why is dimensionless? What does it even mean? Well, you can see friction, you can see another force, normal force. So this is in newtons, that's in newtons, and that cannot have any units, right? If you have a unit, then you combine with a Newton's unit, you'll no longer become Newton's unit. So you have no unit, that means dimensionless, or just no units. It's a fraction between two variables with the same exact unit, so they cancel their units. Thank you.